the design example to go along with that. So to start off with, where we finished off with our example was we went through and calculated our KL over R. And we get 43.3. Again, this is less than 100, so we're okay using our simplified approach. Now we're going to go through and calculate our what I've been calling KL over R max, right, to determine whether or not this is going to be considered slender or not. So I'm going to start again with our M1 to M2 ratio. So in this case, we've got 20 over 215. And this is going to give us a positive value in this case because of single curvature. Right? So again, this is bigger than minus 0.5. Since it's positive, it can't really be less than that. So we're going to stick that on into our formula for our KL over R. And I've been calling this KL over R max. So 25 minus 10 times our M1 to M2 ratio, divided by square root of TF, F prime C, and area. Again, just as we had last time working with the that new set of compatible units in here. And this calculates out to 32.8, which is less than our 43.3, so therefore slender. Now we went through a process in our first example where our calculation came out to non-slender. So when we were using our interaction curves, we just ended up calculating based on our M2 value. So now with slender, what that means is we have to take into account our P delta effect. So that means instead of calculating MF or M2 over AGH down here, it's going to be MC. So we have a little extra calculation. So what I'm going to do is I'm going to start by looking at our tables. Putting it up right here. So we're going to start off of we already did that part. We looked at this one and said we need a reinforcing ratio of about 1.5%. We looked at this one here. So I'm going to look at reinforcing on all four faces. So that's going to be this table right here. And we're looking at a 450 by 450. So we're up into this region here. And again, I want to overestimate a little bit based on needing some moment calculation, right? So the value for rho that we had picked up before, about 1.5%, was just due to axial alone. It doesn't take into account the moment part of that. So we want to overestimate a little bit. So where I'm going to start off with here is this value right here. So this is going to be 830 M bars, giving us a reinforcing ratio of 2.77. Right? So that's a little bit higher than our 1.5 that we started out with. Yes?
I have a question about slender versus non-slender. Do you tend to use reinforcing on two faces if it's non-slender and four faces if it's slender, or is there no...
There's no real difference between the two, yeah. So what it is that, and we haven't really shown this calculation here because we're looking specifically at square columns, but if you have reinforcing only on two faces as opposed to four faces, then essentially your rectangular column is behaving somewhat like what you get with a rectangular column, where I've got different bending in one direction versus the other direction. So in the one direction, all of that reinforcing is effective because it's away from the neutral axis based on that gamma gauge distance. But in the other direction, bars that are on the outside edge are effective, but ones that are in the middle are not effective. Ones that are in between there are somewhat effective, like we were talking about with our I calculation before. Right, so the process going through with a rectangular beam is not that much different. It's just we have to look at the bending in two directions separately.
So is it going to be more of an architectural decision if you want to have a long rectangular section? Where
architectural decisions certainly play into it, but there are practical engineering type decisions. Right, so for example, if you're trying to build a parkade, right, or an underground parking level in your building, right, if you put in rectangular columns and you orient the direction of the rectangle so that they line up with the spaces of your parking, then you fit more parking spaces in. Whereas if you rotate them the other way around, it'd take up an awful lot of room, and you've now got more space between cars, so you get less parking spaces, right? So that's a practical difference, but architectural decisions can come into play as well. Okay, so as we go through here, our first guess, let's write this down. I'm going to try 8 30M bars on all sides. And this gives us a reinforcing ratio of 2.77%.
So here, I just have a question.
Yep.
So this is 4 faces, right? Table 7.4.
Yep.
So how can you turn it off the parameters that you give in a question that it's going to be a 4-face or a 2-face? Like, which table you use then?
Well, to some extent, it comes down to with what your target reinforcing ratio is that you're aiming for. The higher the reinforcing ratio, the more likely you're going to have reinforcing on all 4 faces. Right? If your reinforcing ratio is relatively low, then you can get away with doing it on 2 faces.
Okay.
So in this case here, we're going with 4 faces. The first example we used 2 faces, but that's a judgment call. I could have designed either example using either 2 or 4 faces.
Okay. And the second question is, you picked 2.77. Yesterday, an example, you just picked slightly above. It was like a 2%, 2.4.
Yeah, and this one's quite a bit more.
Right, and you're accounting for the moment you're saying, or something?
Yeah, that's right. So what we've got is the first table we looked at, where we came up with 1.5%. Was based just on axial load only. Right? And it doesn't take into account any of the bending. How much you take into account for bending is dependent upon the relative size of your moment. Right? Because we know when we're looking at our interaction curves, go back to this. When you go back to your interaction curve here, right, this line here is your axial coming across here, and this doesn't change, but it gets dropped off down here based on the shape of this curve for your moment. So if I have no moment, right, we're just looking at these straight lines. Once I have moment, and I'm coming across here, right, you can see that we end up having something which is quite a bit different, right? So this, right, if I come across here, if it were just axial, we'd say 1% works. But now bringing in a moment, now I'm getting to a point where I need something like a 3%. So depending on how much moment you have, the further you are out here, the more reinforcing you end up needing. You kind of have to take a bit of a look at how much dead load you've got compared to how much moment, and take kind of a judgment call. Right, so what we've done here is we've almost doubled the amount of reinforcing based on just axial load alone. Right, so that would account for, right, if I just look at this curve here as an example, right, if I take this curve here and I double our reinforcing ratio, well, that takes us up to about here, right, this will account for, at the same kind of level, you know, a certain amount, approximately, of moment on the system. Right, if I have more moment, I'm going to need more reinforcing. Right, so it's a guess at this point, right? And you'll see in this particular example, even though we have overestimated, it's not going to work out for us, and we're going to actually have to go through and iterate this process. Right, so we're going to next go to our table that tells us what gamma is for this particular configuration. This table right here. So we're looking at 450 as the size of our column, and so here's our 450, and we're coming across here for 30 M bars, and I'm pulling off a value here, a gamma of 0.71.
Is that for square columns only?
No, and rectangular, but so I could have a rectangle that's 450 in one direction and 600 in another direction. Yeah. Well, not minimum, you'd have it in each direction. So for a rectangular column, you'd have to check both directions separately. And you typically have, so this is table 7.2. Gamma 0.71. Right, so if you've got a rectangular column or a column where I'm dealing with reinforcing just on 2 faces, even though the column might be square, you'd still have gamma, it would be the same for a square column with reinforcement on two sides only. But the analysis of it, you have to consider the bending in two separate directions. So typically in your frame analysis that you do with an S-frame, in order to figure out your moments, you'd be looking at two values at the same time, right? Or two different analyses, one in the north-south direction, one in the east-west direction. In a more complex structure, you may have a few extra frames that you have to analyze in there. Right? So now, off of this, we're able to determine which of our interaction curves we're going to use. And remember we said that rounding down is going to be conservative, and this is pretty close to the 0.7 anyway, so I'm just going to use the appropriate curve for the 0.7. Now before we do that, we have to go and calculate our PC. So let's go find our table here. So we're looking for an FRIC of 30 and 35 MPa. So scrolling down here to find there's 30 MPa and 35 MPa, 0.6. Here's our 0.7 curve right here. Right, so this is the curve that we're going to look at. Right, and we started off here with a reinforcing ratio of 2.77%. Right, so what I'm going to do here is I'm going to start by interpolating a curve in between our 2 and 3. So there's 2 there, so 2.77 is coming in about here. So there's our 2.77%. Now, in order to figure out the point that we're going to be plotting on here, I need to be able to calculate our MC. And again, this is our moment divided by AGH on the bottom here. So I need that MC value. And that MC value is going to be dependent upon the Euler buckling, which is dependent upon EI. So what I'm going to look at here is the two values for K that we have right here. And I'm going to interpolate the value for K in between there based on our current percentage level of 2.77. All right, so we're going to start here and come up with a K value. So 2.77 minus 2 divided by 2 minus 2 times the difference between our numbers. So that's our 944 minus 777, and then plus our base level. Wrong number in here, and I have to recalculate it. That should be 7. Gives us 906. I'm not worrying about decimal places in here. So now we're going to calculate our EI. And the EI we're using is based off of this formula right here. K VH cubed divided by 1 plus beta D. So we're going to calculate our beta D term. Again, this is factored dead load, so 1.25 times our dead load divided by PF. And this is equal to 0.49. And now I can calculate my EI. 906 times 450 times 450. Our pH cubed divided by 1 plus beta D, 1.49. And here we get 2.493 times 10 to the 13th. It's Newton millimeter squared is the unit. Now we'll calculate our PC, the Euler buckling. So pi squared times EI, 493 times 10 to the 13th. divided by KL. Squared. Right now, what we've got here is a value in terms of newtons and millimeters, right? So we've got newton millimeters squared here. I got millimeters squared at the bottom, so we're getting newtons out of here. So I'm going to put in a unit conversion factor and multiply by 10 minus 3 to turn that into kilonewtons. And we get 718, 790 kilonewtons. Okay, in addition to PC, we also need CM. So our CM calculation, 0.6 plus 0.4 times our M1 to M2 ratio. And of course, this has to be greater than 0.4. Next, we plug in some values here. 0.09. This works out to be 0.636. MC formula is our CM times our M2 divided by 1 minus PF divided by phi M and PC. Now we have all the components to stick into that formula. And so we got our CM, 0.636. Our M2 is 215 kilonewton meters. 1 minus our PF was 3825 kilonewtons and divided by 5.75, and PC, which we just calculated, again, it's kilonewtons. All right, so units cancel out here with our kilonewtons. .4 kilonewton meters. And again, this number is bigger than M2, so it is an amplification, which is what we expect. Now we're going to calculate the two criteria that we're going to plot against here. So our PF over AGH and now our MC over AGH here. So our PF over AG, 3.825 divided by 0.2025, 18.9 MPa. So we're going to start by putting in that line. So that's about 19 MPa, so that kicks in about right here. Now we'll calculate our moment over AGH. So it's now MC over AGH. Again, 470.4 unit conversion factor. 0.2025, 0.45. So So we have kilonewton meters in here, and we have meters in here. So everything's working out in terms of kPa. So our 10 to the minus 3 there converts that back into MPa. Okay, 5.16 MPa. So now we're going to plot that point on here, 5.16. So 5.16 is about right out here. So there's our point, right there. So when we take a look at our curve, we're going to say, does not work. Right? The point lies outside of the curve, so it does not work. So we're going to come up with a new configuration here. Now, what we want to do here is adjust the amount of reinforcing. Now, you might